Now let's talk about the speaker today. I'm happy to introduce Z to all of you guys. He's a postdoc fellow at Stanford Doe School of Sustainability. He finished his PhD at University of Oklahoma in 2022. His study basically focuses on surface water across scales. He has worked on flood predictions, for which he uses frequently remote sensing data sets coupled with models. And he has over 30 peer-reviewed journal articles. His work has been featured in some of the mainstream news media channels like New York Times, CNN, and so on. And today he's going to talk about remote sensing in observing hydrologic cycle. So I'll stop there and over to you, Z.
All right, so hope everyone can see it. Um, yeah, it's my great honor to be here and presenting some of my previous work and get to know folks a little bit more. I know you have a diverse background, so this talk I'm gonna be very entry level, less mass, and hope you enjoyed it. Then the topic of my talk today will be remote sensing observing water cycle, hydraulic water cycle. So a little bit background on myself. I came off as a hydraulic engineer for a bachelor's degree back in 2017. And then I did my master's in TU Delft in the Netherlands and the National University of Singapore for water resources management, where I conducted my master's thesis in genetic programming for hydraulic model structure and parameter optimization. Then right after that, I worked as a data scientist for a brief 6 months, then decided to move to academia. Then I applied for a doctoral program at the University of Oklahoma, uh, where I studied the remote sensing in water cycle, as well as developing some flood models, hydraulic models, then applying those models to investigate how the current climate change impact on flash floods. Then after my graduation, I got an offer from Stanford to further my research, investigating how those floods may have impact on local communities. So that is to say, my research really has three pillars. One is data, one's model, application. For the data part, I extensively use remote sensing observations to monitor the water cycle. And I also developed some flood database to analyze flood risks. For the model part, I developed a hydraulic model for better flood prediction. Then realizing large-scale hydraulic simulation is a big issue or one unanswered questions. Then I shift my research a little bit to like real-time and large-scale floods or stream flow hydraulic simulation. And finally, by applying my data and models, I looked into how future flash floods might occur, given a warmer climate, then as well as analyzing the spatial temporal characteristics of future floods. Finally, I think my research focuses a little bit more on the people-centered impact. That is one part being discussed heavily recently, that is climate injustice issues. I work closely with Native Americans when I was in Oklahoma. We established two-way communications with the local people, trying to help them build capacities and understanding how climate might impact on the local tribal nations. Then moving to Stanford, I was looking at how flight impacts on human mobility and global health. So if you are interested in any one of those topics, just let me know. We can discuss more. Then today, of course, this is a very diverse projects, but we're going to only focus on the remote sensing for water cycle. I think most of you are very familiar with water cycle chart. Here, a little bit different is we had a perceptual diagram, meaning we quantify the number of water being transported from ocean to atmosphere to land from given those observations from 2002 to 2008. So there are two physical quantities. One is the flux, which is showing here as precipitation, as evaporation that is given of how much water per unit time, let's say for 1 year. And there's another physical quantity, which is state. That's how much water present at a particular time. That's, so for instance, the ocean water and surface water, groundwater. And from there, you can see those are quantities. Ocean basically contains over 70% of the global water as compared to surface water. And that's a nice thing about understanding the water cycle on Earth's surface. So this is a brief question to you as an entry point, that what is the most fascinating part of water cycle for you? You don't have to be an expert in your analyzing the particular water cycle component in your research. Just interesting, how do you perceive those different water components, and what is drawn to you mostly? Maybe if you can just put in the chat, just get a better understanding of people's background and interest. I'll give 1 minute here just to have your feedback. All right, so that's pretty much evaporation, precipitation, transpiration, soil moisture. That's the flux, right? Most people are interested in. So today, I know it's impossible to cover every component in the water cycle. So I particularly choose one, which is the major component. As you can see, the land precipitation, ocean precipitation in total can cover over 500 cubic kilometer per year water flux from ocean to from the atmosphere to ocean or on land. And we're going to focus on that as a main theme for today's talk. Then, as you may say, we wanted to get the precipitation in the right amount. Either too much or too little can cause troubles. If you have too much water, that's basically you got a waterlogging in the city, inundation, and people lost their lives because of flooding. If it's too little water, cause a lot of damage to the agriculture, crop yield, etc. So we wanted to understand how much water is falling as a precipitation to the Earth's surface. Then it comes to the question, how do we measure precipitation? So this graph shows three conventional ways to measure precipitation. One through rain gauge, and through weather radar, and the satellite. So the most longest record is from a rain gauge, where you can basically record the water volume for given particular time, and you can translate that water volume per time to a more instantaneous value, let's say 1 millimeter per hour. And weather radar, just since World War II, people are realizing there's an influence from weathers to using radar to detect the aircraft. So they start using radar to extract that weather signal and convert it back to these rainfall rates. So as you can see, radar scans the atmosphere instantaneously, and you can get basically the instantaneous rainfall rates inferred from weather radar. Then finally, the satellite, after I think 1970s, people are starting to send a lot of rocket satellites into the space in order to understand how the water is distributed over the Earth's surface. And the satellite can have a bird's eye view on the precipitation or the whole water cycle. As to say, it has a very abstracted view, and it helps us to understand the water distribution or redistribution over the Earth's surface. Then another question here, which product have you used in the past in your research, or which product you are mostly interested in? Perfect. So I think after today's talk, you should be able to have a sense of the kind of pros and cons of each product. As we know, no product is perfect, and they are constrained by a lot of limiting factors. And hopefully, after today's talk, we get a bit better understanding of different products. I will get into more details of those individual products in a second. All right. So if you map those precipitation sensors in terms of two dimensions, one is the resolution. The resolution could be spatial resolution, could be temporal resolution, right? And another dimension is the space-time representativeness. That's basically how the coverage of each individual sensor can detect. So you can see rain gauge is sitting at a position where you have very high spatial resolution. That's a point source. It pretty much just only represents that point, how much rainfall you received over the last period of time. So it has a very poor space and time representativeness. For weather radar, it sits between rain gauges and satellite. Typically, for a weather radar, it can have a resolution of 250 meter, and it can cover over 200 kilometer in space. And for satellite, of course, it covers the whole globe, Earth, but the resolution is poor. So the most advanced satellite algorithm has half an hour temporal resolution and they're about 10 kilometer spatial resolution. So let's break it down into individual sensors. For rain gauge, the mechanism is pretty simple. Here I'm just illustrating one particular type of rain gauge, which is called a tipping bucket, where it records or collects rainfall, just holds rainfall in the bucket until reaching a point when it can dip the water out and record the time that that amount of rainfall was recorded. So as you can see, the rain gauge only records the water volume. At that point, the limiting water volume is reached. So that's a cumulative rainfall over a particular time. And as for its resolution, it varies from minutes to days to months according to how you're going to report or how the threshold is set. Like during a dry period, it could be over a month until it reaches that tipping point. But during that dry period, a lot of water is going to be evaporated. So there's a huge limiting factor for rain gauge. That's a limit from evaporation. And the sampling surface, that's about 15 centimeters. So I just showed you the space representativeness of the rain gauge is quite poor. Then there are plenty of distributed rain gauge products over the globe where you can just plug in into your research if you're interested. I would say most of the rain gauge products are designed for climatological or climate analysis. So they have a pretty poor frequency at monthly, daily, and the resolution 0.5 degrees. And I have to mention another limiting factor is that because the rain gauge only has a point source, when you grade those rain gauge networks, you have to either interpolate or extrapolate. So the uncertainty brought in by interpolation and extrapolation is another head topic in your research. So you have to bear those uncertainties in mind. And unfortunately, as you can see here, this shows the number of stations evolving over time. So those rain gauges are really, number of rain gauges is declining after about the 1970s. So that's another factor that the rain gauge products is not very popular today because we had a lot of drop down of those rain gauge numbers over the globe. Then the second part is weather radar. as I said, only since World War II, people realizing that we can use weather radar to detect some weather patterns, even infer the rainfall rates from the radar signals. So what does it do is that the mechanism of weather radar is that it transmits those electromagnetic waves to the atmosphere. And when the signal bounces back, it receives it. It can measure how much energy or signal lost during that interference from the clouds. Then based on that, you can basically infer the relationship between, that's what we call the radar reflectivity, the relationship between radar reflectivity versus the rainfall rates. You can get popular ZR relations such as Marshall relations that translate reflectivity to rainfall rates. And a nice feature of weather radar is that it not only transmits horizontal waves, pulses, but also the vertical pulses, from which you can basically interpret the shape of the hydrometeor or the precipitation. Let's say the rainfall, raindrops versus snowflakes versus grapples or big drops. So the advantage of differentiating those different types of hydrometeor is that you can get a better relation between the radar reflectivity versus the precipitation rate. And the resolution of the weather radar just varies between 2 minutes to 15 minutes. So, but at the individual radar site, you can get a pretty high sampling resolution at 250 meters. Here, that shows a very typical degraded radar product that we have in operation. Then the range, it can reach as far as 200 kilometers, but you will suffer from the beam broadening issues if you get over 150 kilometers. Then this table just shows the radar product we can utilize in the United States. Uh, Three very commonly used radar precipitation product. One is the MRMACE, which is a multi-radar, multi-sensor product. It has a spatial resolution of 1 kilometer. The temporal resolution in the very fine resolution for flash flood forecast is 2 minutes, but for the gauge adjusted precipitation product, it can have a resolution of 1 hour because it has to wait for the gauge data to come in and correct the radar signals. So it has larger data latency. For the period, it right now has two like different periods. One is from 2001 to 2011. That's a reanalysis product. The other more advanced, more operational product is from 2014 to present. The source is from NOAA, National Severe Storm Laboratory. And we also have a stage 4, which has a little bit poor resolution, 4 kilometer. The frequency is from 1 hour to 24 hours. It has covered the whole US and the periods from 2001 to present. Then if you wanted to have a better look at your individual site, let's say if you want to forecast a flash flood in your study area, which is not like covering the whole continent, you can use the individual radar product that is an X-RAD level 3 data, which has very fine resolution, 250 meters, frequency of 5 minutes. And for some individual site, it has started from 1990s to present. And people have used that a lot for those localized storm forecast or flood prediction. Then finally, the last of the three products we're going to cover today is the satellite product. the satellite very similar to radar with a radar. It just sends those electromagnetic wave to the Earth's surface, then receives back the energy. That's for active microwave, which the radar is which the spacecraft is carrying those radars. And another way is a passive microwave, because as you know, every object on Earth has a brightness temperature. So what the passive microwave does is to only collect the information from those objects, the temperature emitted from the Earth's surface. So it doesn't require much energy to send out those radar waves. And there are some popular, very valuable precipitation products over the globe. GPCP is one commonly used for climate studies, and TRIM, GPM, those are like buzzwords in satellite precipitation community. Especially the GPM, that is a go-to satellite product, has the highest 0.1 degree resolution and 30-minute temporal resolution, covering 60 degrees south and north from 2015 to present. But actually, the iMerge product has extended back to 2000 or so. And actually, there's another category of precipitation or graded precipitation product, which is from the reanalysis product. The reanalysis product is from the model simulations, and they constantly using those observations, injecting those observations into their model, a simulation framework to correct the model simulation. Those are very valid and widely used satellite precipitation products. I just wanted to briefly mention here if you're interested. The nice feature of you having those reanalysis products is that you can pretty much get all the information from the atmosphere. You can look at the water vapor, you can look at those air, temperature from different pressure levels in order to kind of dive a little bit more into how the storm structure is formed over time. So to speak, those products are not accurate as you thought. So for rain gauge, if we put into context of extreme weather events, for instance, hurricanes, thunderstorms, tropical cyclones, because of the strong wind, that's gonna carry a lot of water rainfall away from the site it's supposed to be collected from the rain gauge. To some studies, the wind-induced loss of rain can reach up to 50% high. So imagine, let's say Hurricane Harvey dumped over 1,000 millimeters of rainfall over a particular region, then the rain gauge only gives you 500 millimeters. Then that's a huge bias, right? As compared to what you really measured. Then for radar, because it's not a direct measure, it's what it measures is the reflectivity or the signal back. Then you have to infer the rainfall rates from the radar signal. From there, as you can imagine, there's uncertainties from the equation you're going to use. There's uncertainty from either the radar signal is really from the weather. Sometimes you can get non-weather signals, like for instance, those bats or birds that could typically detected by weather radars, then you thought that would be a weather signal. And of course, there's a difficulty or a ongoing research on identifying different hydrometers. I've talked about the importance of differentiating different hydrometers. For rainfall, for snowflake, for hail, you might apply different ZR relations. And of course, if you wanted to use your radar product in those mountainous regions, you have to be very cautious because those radar waves is going to be intercepted by those mountain ranges. Then you might not get a very accurate rainfall results. And finally, goes to satellite. It has the most indirect and infrequent estimates as compared to rain gauge or weather radar. So typically has a larger uncertainty as compared to the former two. And even worse, when you consider using a one product for your hydrologic simulation, let's say if you want to use a forcing precipitation forcing for a hydrologic model simulation, and a little bias or a shift of some amount of precipitation is gonna accumulate into your stream flow simulation. That's the error propagation issue. So that's another caveat you have to bear in mind when applying for choosing different precipitation products. You want to be representative as much as possible. And here just shows an example of using different precipitation products for hydrologic simulation. As you can see, the very first, the MRMS is a radar product, the red line here. It just over predicts the whole stream flow as compared to the observation in gray shaded region. So it could be due to the non-weather signals because during I believe this was in a Hurricane Harvey event. So there are a lot of debris brought up in the air by the very strong updraft of wind. So very likely that it's not only from the weather signal, it could be other noises. Then the second one, it just shows radar predicts higher peaks than other two products. Then it's becoming closer to the real observation. So a little difference in the precipitation products can produce totally different and accumulating effect on the stream flow prediction. So with that being said, understanding the quality of each product is the key. But unfortunately, we don't have the ground truth. Thinking of which product would you trust more? Because I mentioned there's no perfect product, and it takes takes some efforts to validate the individual product. When you are in the position where you have no idea which product you should choose for your study, then it becomes a puzzle, and research people are trying to figure out in under certain circumstances which product should we use and how much uncertainty is brought in by different individual product. So another question here, thinking of an extreme event like Hurricane Harvey, which product would you choose for an event? So far, we've talked about the uncertainties of individual product, and just based on your instinct, which one would you opt for? Just curious your answers.
Z, meanwhile, everyone is requested to answer in the chat, but there are a couple of questions maybe you can answer while others are sort of answering your question. Um, so one of the so the first one is not it's more of a request than of a question is if you can there are folks who are not from hydrology, so maybe
Mm,
terms could be a little complex for them. So
mm,
the request is if you can break it down a little bit more for non-technical people.
mm,
Um, so that might help. That was the first request. And the second one is a question which goes like this. Since there is a lot of trust issues on rain gauge, radar, and satellite data for precipitation modeling, is there a way to deal with these uncertainties? Is hybridization possible?
Mm-hmm. Yeah, sure. Just to step back, what is remote sensing? So as you know, we all humans have different senses, right? We have eyes, we have uh, hands, we can touch, we can see things, we can touch things, we can smell. So remote sensing is like consider it like a human eyes. You basically observe things from a distance. You are not like rain gauge where you just collect the data and record it. That is basically based on how much water you collected over a period of time. But like radar is sends wave to the atmosphere and reflects back. That's like human eye. You see that's a big chunk of cloud in the air, and you can briefly, based on your experience, like you know it's gonna rain. So that's what I call it remote sensing in very uh, layperson words.
Just to add on that, it might also help. So when I got introduced to this, it was sort of complex how, for a layman to understand how these satellites and radars are able to observe water in any sense. But the truth
Mm-hmm.
is they do not see water. What they sense is the energy. And as Z was talking about a ZR relationship, that is nothing but you can imagine there are like there's an x-axis where you take your energy that is being measured, and then y-axis is your target of interest. For example, here it is precipitation, and you try to fit a relationship between the two. So the satellite is actually absorbing the energies, and that is being converted to the amount of water that could be there, which might have potential precipitation. For example, one of the products that Z touched upon in remote sensing is TRIM. So what these satellites, some of them, not every, but some of them, what they see the top of the cloud. And once what happens is the top of the cloud radiates some energy back to the sensors. So that energy, which is being taken back, is sort of converted into how much precipitation might be expected. I think, Z, you can add, or if that's not correct or something.
Yeah, that's totally that's what we described as a geostationary or infrared satellite because the those particular type of sensor cannot penetrate the clouds, so you can only saw the cloud top temperature. But imagine that you just like human eyes, you observe there's a cloud high in the air, and based on the color of the cloud, which is basically how those lights are blocked. So you might think there are a lot of raindrops in the clouds, and you can construct your relationship by yourself based on the color of the cloud versus the rainfall rates is gonna happen in the next 5 minutes. That's remote sensing as well. So satellite is nothing but using another wavelength trying to interpret the things happening in the cloud. That's an analogy I can think of.
Yeah, and the next question was if there is a lot of trust issues on these kind of data sets, be it rain gauge, radar, or satellite, is there a possibility we can use hybridization, like mix of everything, to come up with or
Yeah,
quantify uncertainty?
that's our next talk, second half of my talk, which is to introduce a way to quantify those uncertainties. And of course, you can build up on that using the uncertainties you quantified, trying to correct different products, trying to bring up a new merged product that has the strengths of each individual product while reducing the uncertainties. All right, is there any other questions?
We don't have any questions as of this moment, so we can continue.
Okay, perfect. I saw a lot of answers. Uh, they more inclined to use reanalysis datasets. Interesting. Yeah. Because maybe because I didn't touch the uncertainty from reanalysis but datasets, so you might thought reanalysis data is more impeccable. Anyways, for the second half of my talk, I'm going to introduce a mathematical framework which can quantify the uncertainties of those individual precipitation products and build on which you can, of course, extend that to correct the different products. So here the framework is called triple collocation. It's not a new framework, has been used for a while for different applications. So people have used that in soil moisture. If you have three individual soil moisture products, have been used that for wind product. So as basically for all the Earth system science applications, you can apply this framework if you have three individual products and you think the errors of those products should be independent and unrelated. That's how you wanted to bring different sensors or different measurements. So you assume those errors are independent and the expectation of the error is treated as zero. Then below is a linear error model, in which those x terms are perfect estimates of rainfall, and you can always transform your measured rainfall into a perfect measurement for each individual products. So there's a linear relation built on that. Then you can pretty much get into those we call the triple errors and triple correlation. That's nothing but calculating the covariance of either two individual products. That is to say, when you have three products in the same room or in a table, you can justify which product has majority vote. It's like a voting system, right? If only two products, you cannot determine which product you want to use because there's just 50-50. If you have three products, then you have the majority to vote, I say 2 versus 1, voting for gauge, then you pretty much know the gauge has less uncertainties. So what I'm talking about here is not has no absolute error, though they are very pretty much that's relative. So the triple error just estimates the uncertainties or of individual product. R1 is represent one product, R2, R3 products, the second and third product. Then you have the triple correlation that is more of a metric to represent if you have less uncertainty in individual product. So today, that's for the coding session. Should we have a brief break? Or I can answer questions if you have for the whole framework or what I've
So
discussed.
I don't see questions right now. So maybe we can take a 5 minute break, and then if after this, or you want to explain this and then take a break, I don't know. It's up to you.
Yeah,
Or
it's
we
in a coding session. We can take a break from now, just get some water.
and I
Mm.
think Z, we can get started.
Yeah, even for those questions I've answered, if you just want further more explanation, just feel free to type in and I can explain more. All right, so here is showing the whole the coding session workflow. Just wanted to get everyone on the same page and of understanding the whole picture of what we're going in the next hour. So the coding or practical session is gonna apply the triple collocation method to understand the uncertainties for each product, and hopefully we can get to know to answer the question I posted earlier, which product would you choose for an extreme weather event? Then, of course, the very first thing is to select the domain. As you may be doing research, That's how to select the research site is very important at first step. Then we're getting to download the data. By the way, I just shared two resources in the chat. One is for my GitHub page dedicated for this workshop, where you can find a script to download the data. And second one is a Colab Jupyter notebook, where you can basically uh, execute just follow my steps. Then after downloading the data, we get into the geospatial processing. We wanted all the products on the same grid space as well as the resolution. So we'll clip those products to the research domain you have chosen and do the spatial matching of each product. Then finally, we're gonna use the GDAL program software to do the geospatial processing if you are familiar with GDAL. And finally, we'll get to the triple collocation processing using the Jupyter Google Colab. For this TC processing, we have two different levels of results. One is region overall, basically just showing you how is the overall performance of each product. And then we'll get to the grade level where you can basically see the spatial distribution over a particular region that this product performs better than others and vice versa. So the example or tutorial I prepared is for Hurricane Harvey, but you can essentially apply for other regions or other events. For Hurricane Harvey, I don't think I need to emphasize the importance. It caused a lot of damage to the Texas, Louisiana, Oklahoma, those regions. And the geographical region boundary I've selected is picked here. So for the satellite data, we're going to use the iMerge product. That's arguably the best satellite precipitation product so far we have. And this link points you to the page where you can download the data. And there are some instructions how you can download data using wget command. If you're using a Linux system or Mac system, you should get those commands. For Windows, you have to download, I think you have to download the software in order to download data. Then for the radar data, we're using the multi-radar, multi-sensor product. As I introduced, it has a 2-minute temporal resolution and 1 kilometer spatial resolution. So I have a script download mrms.ch where you can use that to download the data for the Hurricane Harvey period. I think I have provided both the Linux version and Mac version of the script, so feel free to try it out. Then for the gauge data, we're going to use the NSAPE gauge only data. So I have to mention that all those data sets have to be from one single source. For instance, the satellite data, we're using the uncalibrated. The calibrated version that has mixed with gauge data, so we cannot guarantee the error term is not correlated. So we have to use the individual data source. And so after we get, don't worry, I already provide you with those data sets in my GitHub repository, so you don't have to do this yourself, but feel free to try it. It's just get you familiar with downloading those remote sensing data. And get into the geospatial pre-processing, we wanted to bring those products on the same page, having the same grid spatial resolution and the geographical extent. So what we do here is, this one is an example for unsafe gauge only product. We loop through the file name, which ended with grip file. The GRIP file is a particular type of format for the weather data. If you have used any weather forecast data in the past, you probably get familiar with the GRIP format data. So the GDAL can support to read the GRIP files. You don't need to worry about decoding those different types of data. So what we did here is to warp the geospatial, like we wanted to have the same reference system. We wanted to bring them to EPSG 4326. If you have learned the geospatial fundamental like just GIS 101, you know there's many different types of geospatial systems, and we wanted to bring them all to the same geospatial system so that we have the grid representing the same grid cell. Then after that, we translate to a 0.1 degree resolution. The reason we're using a downscaling instead of upscaling instead of downscaling is that we hope to bring them all to the native resolution of satellite data sets, because the satellite has the coarsest resolution out of three. It has 0.1 degree, and both gauge and the radar products has 4 kilometer. Radar has 1 kilometer. Gauge has 4 kilometer resolution. So we use an average upscaling algorithm to have to bring them to the same resolution. I saw one question here. Let me see it. So the question is radar data global too? For example, NASA satellite data covers the whole Earth. Does radar do the same? The answer is no. Well, it depends on what kind of radar data you're talking about. If it's for ground weather radar, no. I know because radar data is quite sensitive. It initially was used for military use, right? So a lot of countries want open source or open publicize their radar data. So that's a big issue. But in the States, we're fortunate we have the radar data over covering the entire continent. And if you're talking about the spaceborne radar, that's a different story because the satellite can carry radar as well, right? So those spaceborne radar covers the whole Earth. Yeah. All right. So this just shows you how to upscale the gauge product as well as just having the same geospatial extent. So later on, when we process the data using triple collocation, it's easier for us to manipulate the data. Then this is down for multi-radar, multi-sensor product, the radar product. The same thing, we just transform it to the same geospatial system and then do the mappings, matching to 0.1 degree resolution and crop it to the same geospatial extent. All right, I think next we can get to the Colab Jupyter Notebook. Let me reshare my screen. Meantime, let me know if you have any questions. If you try out those scripts I provided in the GitHub, maybe we can take a brief look at the GitHub repository and just show you guys what is inside, right? So hopefully you can see my GitHub page. We have already processed those data sets, so you don't have to do it yourself, but feel free to check out. So the iMerge data is pretty standard. You order the data from the NASA website, but you have to register for the Earth data so you can download data on your end. Then there's a script to process the data. That's for the satellite data. And for radar data, the same. I just provided two versions of the scripts. One is for Linux and one is for macOS. There's slight difference in terms of those command for different system. You just need to change the date time according to your research of interest. If you want to do another extreme weather event, feel free to change that, and it will just download the data from your terminal end. Then finally, the gauge data, uh, the same, the process, that's pretty much what I have covered before. Stop here. So one more question. The question is, if satellite collects data at 30-minute interval, radar at 1 hour interval, and rain gauge at 15-minute interval, is it still possible to accomplish triple collocation using three techniques with varying timing? Yeah, what you need to do is really just to find a collocating time frame where both or three of those products are available, have the intersection of the three products, both spatially and temporally.
It's just to add, it's more like finding the common factor. So maybe 2 hours is where you will find everything. So
Yeah. Let me share another screen. We can get to the collab. So another question. Okay, another question. Just comment. All right. So let me know if the font size is too small. I can adjust that. Otherwise, I will just go ahead. So if you are familiar with Jupyter Notebook or Colab, Google Colab, essentially those is already formatted coding cells. You just need to execute those cells yourself. There's a little play button on the left. You can click it. After it's clicking, basically it's saying it's running the code, and you can do a shortcut your keyboard that is Control plus Return for executing the code. Or if you wanted to execute all the codes, you can do click the runtime and run all. So that will execute all the codes. Okay, we'll get into those code step by step. Then the very first one is nothing but download the data I've showed you before in my GitHub repository. I just cloned the whole repository in the folder. If you click on the folder icon, there's a folder called the 2024 Summer School. You expand it, then that's what we saw in the GitHub. It has all the data already processed, and it even has the script used to process the data. All right, and the second cell is to install some Python packages. What we will use here is the ZAR data, which is particular data management tool that it's a data storing format that helps you to store data or load the data efficiently. And the X-array is a data management tool that's particularly good at manipulating the netcdf data. And CartoPy is a package used to plot those data in geospatial processing and plotting. Then real X-array is a real X-array just builds upon those X-array data, and particularly resolve the GOT file format. Then CTime, that's a time management package. Then after executing this, we can import those packages we're going to use later. So that's we have done all the preparation work. Then the next we'll get to the preprocessing step. What we'll do here is that we define the date range. That's basically for the Hurricane Harvey from 2017 August 25th to September 2nd. At the frequency is at hourly because we process all the data to the hourly time interval to trying to find the intersecting time frames. Then we loaded the gauge data using X-array. That's basically we loop through the time frame and trying to find the file name that matches that time frame. We do the same for MRMS and iMerge. For the iMerge, there's an additional step that I have to resample it because iMerge has a resolution of 30 minutes. So I resampled it to 1 hour using the mean value. Yeah, that's basically trying to load all the data. It's probably taking 1 minute or so to finish. Then the second cell is to make some configuration of my map plot. Use the precipitation color map, trying to configure it that makes your map looks prettier. Run that. And we just wanted to have a brief look at how those products looks in the first place. What we can do is to just to sum them up in terms of time to say how much rainfall was dumped over that period of time. I think it's 7-day period to get a better understanding of the total rainfall during that time. This is what it does. And we particularly had some features there. We added land, ocean, states to make the map look better. Right, this should be what it looks like on your end if you are following me. So the gauge data, that's how the spatial distribution of rainfall is. The highest rainfall volume over the 1 week period is about, I would say 800 or 900 millimeters. And for radar, it's a little bit overshooting. It has over 1,000 or 1,200 millimeters of rainfall for the highest pixel location. But for satellite, it's pretty smoothed out. The highest what it can get to is around maybe 600 millimeter.
Z,
Mm-hmm.
just a quick question. Maybe I did not catch it, but for the gauge data,
Mm-hmm.
how did you make it smooth enough so that all the spatial points were interpolated?
Oh yeah, because we choose the data set that is already interpolated. The way the interpolation is through some optimal, it's like creating one of the interpolation technique that accounts for the uncertainties in individual rain gauges and of course the distance, trying to find the optimal distance weighting. It's already processed. We don't have to do the interpolation or extrapolation ourselves.
Yeah, so I was just assuming that because, then kriging, just doing kriging, it might also sort of bring in its own uncertainty because it doesn't
Yeah,
represent the true picture. So,
yeah, that's true. That's one of the limiting factor of using rain gauge because, as I said, the spatial representativeness of rain gauge is only at that particular point. When you want to have a distributed product, you have to deal with uncertainties from interpolation, extrapolation. But I would say, spatially, visually looking, three products have captured the hurricane or the eye of the hurricane pretty well. And you see the structure of the event, it looks very similar.
at this point, it seems that the radar is catching it much better. I mean, if out of the all
Yeah,
three.
because radar has granular information that has highest spatial resolution, right? What at 1 kilometer. So it might just, but the truth is, you don't know which product is more real.
Yeah.
We don't have a ground truth. That's why we wanted to apply the triple collocation to find out which one has a least uncertainty.
So, okay, that also sort of brings me to another question. So maybe
Mhm.
you'll discuss later on, but let's say you do triple collocation, but then I wanted to understand what do you compare it with? Is it again compared with whether it's able to derive the right amount of precipitation when compared with rain gauges? Like, what is the accuracy
Well,
metric here?
it's a relative error. So like I said, it's a voting system. If two products see at that particular time point, if two products say it's gonna rain 50 millimeter, and the other products records 100 millimeter, they will have less uncertainty for the first two and then higher uncertainty for the last one. So it's all relative. It does not have a absolute measure or metric of which one is better or worse. It just shows, well, what the majority agrees. And
It's
the,
more like reliability, right? What I'm getting
yeah,
from you.
sort of.
Okay.
I saw another question. Is there anything like double collocation? Well, it wouldn't exist for double collocation because if you only have two products, you have no way to figure out the majority, right? You cannot, if it's basically 50 and 50. If one says this is gonna rain 50 millimeter and another say it's gonna rain 100 millimeter, then who would you choose? You have that introduce another more independent or judge to kind of figure out, justify the your choice. All right, so double collocation, never heard of it, but what you can do is have at least three. You can do four products if you found, if let's say for our case, you can bring in the reanalysis data set as well. So it gives you more confidence. All right, I think we should speed up a little bit since we only have 40 minutes left. For triple collocation, I already coded two functions. One is doing the bootstrapping. One is the main function for multiplicative triple collocation. So what it does, I selected the number of bootstrapping numbers of bootstrapping step as 100. You can set it as high. So I think everyone knows what bootstrapping is, right? It's statistical. You basically draw samples from your overall samples to, you can calculate the whatever the metric uncertainty or quantiles, you get a better understanding of your distribution of the samples. Uh, and do the reliability mapping. So what we have here is RMSE, that's a triple error, CC, that's a triple correlation. And for each bootstrap, I initiate those sigma value, R value. The sigma is going to be the, we calculate the RMSE, and the R is for the CC. We draw the sample using the bootstrapping method. The number of samples drawn from the whole population is given here as 100, and the X is my input. You have to do a extra step to reshape your input data in terms of two dimensions. One dimension is time, the other time dimension is product. So in this case, we have three products. So the dimension of this matrix is going to be, let's say, 203 if we have 200 time steps. That's depending on your data. And so this is pretty much following the mathematics we introduced earlier, how to calculate the sigma and R's. Uh, just wrote them down. And finally, because it has so many pixels, it has this different bootstraps, number of bootstraps here, 100. So what I did is just calculate the mean of each triple error and triple correlation. You can do others. You can calculate the like 75th percentile or whatever, since you have the whole distribution of the matrix. That's the two functions right in upfront, and later you just input those apply those functions using your input data. For this cell, what I defined here is the threshold. That's actually 15 millimeter over 1 week. We wanted to only select pixels have received heavy rainfall. For those pixels that don't have rainfall, we don't want them, just exclude them in our processing. And we use a radar as a mask to filter out the pixels without receiving any rainfall. Then we did coordinates just to find out what are the coordinates for the pixels that are receiving 15 millimeter rainfall over 1 week. Remember, we have three products with distributed grades, right? And now we're just downsampling to individual pixels, so that can speed up our processing. But you can just do the whole full-blown triple correlation analysis for the whole pixels, but I don't think that makes sense for pixels without any rainfall or just have minimal rainfall. As well, it is executing. I think it's gonna take several minutes. I'll explain the rest of the code. Then what this cell does is trying to do the triple collocation calculation. So for the coordinates, I call it valid coordinates since we filtered those pixels without rainfall. For those valid coordinates, we firstly select the pixel based on the geographical information, the latitude, longitude, as what is stored in the coordinate. And we use the nearest neighbor to find out the pixel. Then we convert it to the pandas data frame. So if I can show it's processing. Anyways, I just converted to pandas data frame, and for all three different products, then we concatenate them together to form a single data frame contains three columns. One is NSIP, that's gauge, one is radar, and other one is satellite. We wanted to find a common ground for them. That is when they receive at least 0.01 millimeter per hour rainfall, then we only select those time steps above those thresholds. We clip those without less than 0.01 as 0. Then we apply the little step as log transformation because at the error matrix linear model we showed before, we have to, if we want to apply a multiplicative triple collocation, we have to transform our data sets or products into a log form, so you can transform into a linear model. Then just store some latitude and longitude information from my combined data frame. Finally, I concatenate all the data frames in one single data frame. So that single data frame contains all the information, the pixels, the time series of pixels across the region. Still executing. Wanted to show you what DF1 looks like, but let me see. I think we have go ahead because I already pre-run this notebook, so we have those results showing. I can just jump ahead without waiting for them. So after that, you have a single data frame that contains all the pixels information. That's why I say in the processing timeline, or that we wanted to get a first look at which product performs overall better than others. So we combine all the pixels together. Then this is a result. We apply the MTC. It gives you two metrics. One is the triple error, one is triple correlation. So I printed them out. As you can see, the gauge has an error of 0.91 and radar has 0.96. Satellite data has 1.2. As for triple correlation, the gauge has 0.76, radar has almost 0.8, and satellite has 0.4. So for sure, you know, satellite is contains more uncertainties than gauge and radar. When you go back to the plot for the map, you essentially say that maybe that's true because the radar and the gauge look a little bit more closer to each other than satellite, because satellite is underestimating, like they only depict 500 millimeter of rainfall over that period of time. But radar and the gauge overall has over 1,000 millimeter. So you think, yeah, that's probably what we expected. But for either radar and gauge, it's very hard to distinguish because gauge has a lower triple error and has but radar has higher triple correlation. So it's kind of mixed. If you wanted to have a further look on which region the gauge performs better than radar, that's what we're gonna do for the next section. But for the first step, we just know that satellite data is absolutely contains more uncertainties than the other two. If you take one pixel to get a further closer look on the time series and how whether the algorithm, the TC algorithm is performing what we are expecting it to perform, you can pick one pixel. I select here is 145, but you can pick one as long as it's within the range of the number of pixels we have. Then plotted the time series for the whole period. As you can see, radar just overestimates to some extent, satellite underestimates, and gauge sits in the middle. Actually, gauge agrees more with radar in the later half of the peak. In the first half, satellite is closer. So looking back to the matrix, um, actually radar has pretty high triple correlation. Not very high, just higher than gauge and the satellite. And the satellite, because it has more, it shows less rainfall rates, and it agrees more with the rain gauges, so has less triple errors in the end. But that's all for only one side. You can pick more and diagnose those, inspect more of those results by yourself. Then finally, we wanted to resolve the issue that which whether radar or gauge should we choose for maybe different regions, because their matrix look very similar and it's hard to differentiate which one is better. So what we can do is spatially just find the collocating intersecting time frames and put into the triple collocation framework. So that's what it does. We group the whole single data set by their longitudes and latitudes. And for each individual pixel, I calculate the MTC for those three products and appended just concatenate all the pixel, the matrix I received, results I received from the MTC. And I can just basically print out the mean value as well as the standard deviation for the all pixels. So you can see now it looks a little bit different because radar has the same radar has the lowest gauge has the lowest uncertainty and pretty much highest triple the correlation, and satellite now is has as well the satellite has lowest triple correlation, but the RMC, the triple error, is ranks the second. If we plot them in a spatial map, that's what I did here, trying to create a geoframe data frame and just to get the values from those individual data sets, the RMSE and the CC values, then we can plot out the spatial distribution of the matrix RMSE. So as you can see, gauge is pretty consistent over the region. I expect for some high values over the northeast part of the region. And radar has a little bit speckle noises, sparsely distributed. So that's why you cannot completely trust the radar products, because of those some of the noises is brought by non-weather signals. And satellite is pretty smooth over the region. But for the triple correlation, the gauge of course you can see the performance better in these regions which has a brighter values, that higher values, and worse in some of the remote regions where basically you don't have rain gauge, then there's a lot of uncertainties interpolating rain gauges in between. So that error could be brought up by the interpolation method. Then the radar has some validity in those south northwestern part of this region, and less so in the coastal regions, especially in the boundaries between Texas and Louisiana, because I think radar coverage over these boundaries is a big issue there. And satellites basically has some of the lowest correlation value out of three, and so basically you should trust more of those radar and the gauge products in these regions where it shows higher triple correlation. If not, I think that's all for just a short demo of how you can apply the three different products into the framework of triple collocation, trying to understand the uncertainties of each product and get a sense under those circumstances which product you should have more confidence over. And at last, I have some reference for you if you want to dig more into the triple collocation. It does not limit to those precipitation products as long as you have three independent sensors or measurements of something. Could be evaporation, could be anything in the water cycle, groundwater, soil moisture, whatever, you name it. We can just put them into the framework and figure out which one you should trust more. And as a further step, you can, once understanding the uncertainty of each product, you can have your own sort of uncertainty correction or error correction algorithm that trying to reduce uncertainty to merge into a single product that has the benefits of individual sensors while reducing uncertainties. I saw
So,
one.
yeah, there's one
Sure.
question which just came in. Are there specific tutorials on triple collocation for evaporation? I think I can, I mean, you can definitely answer this, Z, but I think this same technique was sort of introduced in the first session by Andrew.
Mm,
Basically, I think their group, and I think one of the references, your first reference is also sort of the triple collocation, which is used for vegetation, water content, and so on. So,
yeah.
uh, yeah, you can sort of give your own answer, Z, on if there are anything.
As far as I know, I've seen studies using triple collision for evaporation. I know there are a huge group of people doing that. So, but in terms of tutorials, I I'm not sure if there's an existing one out there, but you can pretty much just use this as your starting point. Replace the precipitation with your evaporation products. Gotta make sure you satisfy those assumptions, three assumptions. The three products independent, error should be uncorrelated, and the expectation of the error should be zero. As long as satisfying those conditions, you can just pull out whatever products and do your analysis. And another question, besides trim, is there a different rainfall product for the tropics you might know of? Yeah, because trim is already decommissioned, I think back in 2014, 2015, 2014. So it's now it's the GPM era where you have the global precipitation major product is taking over. That's more advanced than TRIM. And TRIM is really focused on the tropics, but the GPM extends to the high latitudes and also works for tropics. That's the satellite. For the gauge, as I listed in the beginning, there are a bunch of gauge products has global coverage. If you want to know the climatological uh, things about climatological rainfall in the tropics, you can use the gauge. Radar might not be available in the tropics in a large scale. But I highly recommend gauge products and satellite products for your depending on your research objectives.
So, Z, I had one question.
Yeah.
So based on your analysis, I was thinking, so obviously you used the early trim product, um, um, but there are problems in this satellite observations for precipitation. That is the main culprit, as you said, I think, indirectly
Mm,
in all of the models, and
yeah.
it sort of propagates to every other component, and then your
Yeah.
sort of prediction goes wild. But
Mm-hmm.
again, still, I think the gold standard is rain gauges. If
Mm-hmm.
you, I mean, what's your opinion? I mean, if there are rain gauges there, that's the only way we are directly measuring water. All others are just
Yeah.
approximations.
Right.
So,
Yeah.
uh,
That's true. But I mean, even though satellites is the most indirect measure of precipitation, also has the most unabstracted view. So sometimes radar has those blind spots where you cannot see this. If for mountain precipitation, you have, and also no gauges out there. There are a lot of ungauged regions in those mountainous spots or complex terrains. So that's when the satellite is the only resource you have. And
and
for depending on different use cases, for climate study, I definitely recommend rain gauge because in the long term it's gonna perform better than others. But the extreme weather, I might doubt it a little bit. Like I just showed, the rainfall loss in during extreme weather events could be up to 50%, unless the gauge is particularly corrected for wind-induced errors. So it's hard to say. I have to say, depending on your research objective or research area. Sometimes
also,
you just don't have choice.
yeah, that's correct. Because you brought on a beautiful topic, which I think it's worth exploring, which is when you go to mountainous regions and high terrains, as you say, there are fewer gauges, and then also it sort of prohibits the algorithm, the radar algorithm, to retrieve the
Hmm.
accurate measurements. Then
Yeah.
is there or has there been any studies, at least in your knowledge, on this is one aspect where you show, okay, if you take Hurricane Harvey and as an example,
Hmm.
and you see which one is performing better. But for example, if there are different types of precipitations, convective precipitations and others.
Hmm.
So for different types of precipitations, which one is better? For example,
Hmm.
is radar better for some kind of precipitation? Is rain gauges much better for other kinds of precipitation, and so on?
Yeah, I haven't seen any research study in that aspect. You guys can carry on that, doing those research, any one of your of the audience here. Yeah, that's the absolutely another application case you can investigate how the storm structure or different types of precipitation for those individual products and which one has higher uncertainty versus lower uncertainty. That'd be, yeah, that'd be cool.
Yeah, and there's another question. I am sort of going to read that. So
Mm,
it's a little tangential to what we have been discussing in the context of surface water quality. What's
mm.
your thought on the role of remote sensing? Does it offer any advantage over on-site sampling, for example, sediments or eutrophication?
Yeah, it's not my expertise in terms of source water quality, but what the right now we have for those optical sensors, which is basically like the human eyes or camera, it can capture the color of your, let's say, a lake or rivers, based on which you can infer the sedimentation or eutrophication of your lake or river. That's definitely an advantage over a on-site sampling, because on-site sampling you can only just get a point measure. You cannot get the relation over, like, let's say how the eutrophication or sediments loading along the rivers has a distributed measure of or the river segments, like things like that. So definitely satellites is playing a big role in surface water quality, and those aspects. It just gives you more information than the individual on-site sampling. I'm trying my best, but I'm not an expert in the water quality application aspect.
Yeah, if
And
anyone in the audience has had any experience and they want to sort of answer, they've worked on this, uh, please feel free. Also, I'm not sure if there are any products because also I'm not so much knowledgeable of water quality, but I think recently I'd seen some of the papers who talk about remote sensing products and eutrophication, and maybe it's worth exploring there. And I think previously someone had asked about tutorials in triple collocation. There are few tutorials out there right now. You can just Google it or see it on YouTube. There are
mm,
lectures available too. So it's out there, and I think people from other disciplines have used it more often than people from hydrology. So
yeah, it's definitely underrated, one of the underrated tools out there.
yes, exactly. Yeah, over to you, Z.
Yeah, just one more takeaway or discussion points after we discussing the how to utilize it. So the first point is that you can pretty much apply this framework for other hydraulic cycle components, so moisture evaporation, etc. That's the one of the main takeaways. And second, paying more attention to the limitation assumptions. I've, uh, I think I've reviewed some papers utilizing TCA without satisfying those limitation assumptions. So that's wrong in the first place. Then I don't have to read the rest of the paper. I know it's totally wrong for when you apply that. Then third, you can use the TCA weights to correct and merge the three different products, as we mentioned. After calculating, understanding the uncertainties for each product, you can apply that as a weight to trying to correct your analysis. There are plenty of papers out there. Just feel free to check them out. Then finally, can we have a quadruple, even quintuple collocation? The answer is absolutely yes. As many products you can bring in, you get more confidence. So you can think of in your the frame your research in that way. It goes on and on. And I don't see many people using like a quadruple or quintuple like collocation for their uh, use cases very often. So you're free to explore that dimension as well. Yeah, that's all for my today's talk, and maybe last some final questions. Happy to answer here.